follow the road around and not do it.
What?
Oh, you just put this up? What do you
Okay.
down, Ro? 12?
Sure.
So today was just kind of a very simple introduction into what light can do depending upon the situation. Today's going to be like two big topics, reflections and refractions. So to kind of give you a visual of reflection. So
Hey! They're talking about money. Yeah.
I'm not.
Wait, let me get my notebook out.
They're not lying.
Actually, just you can keep talking though. Sorry, I didn't mean to just interrupt. I'm sorry.
About that test correction.
No, wait, it's fine.
Whoa, don't ruin it for the rest of us now, Morella.
Okay.
I need it more than all of you.
I need it.
So here's the story. So let's say, for example, we have this laser, right? It's light. Now, so a couple of things that's pretty simple but yet complex. So in this light, when I turn this on, you can't see it until it hits the wall. So if you go through the mechanism on what's taking place, so it's going, as that is transmitted between this light and that wall, it's going through our atmosphere. It's bouncing, hitting nitrogen, oxygen, all these particles that are there, but it doesn't interact with it. Okay, it's just passing through. So if you look at that mechanism, for you to see that light, so it's going to be emitted here, it's going to hit that wall, it's going to bounce off that wall, so those photons are going to get scattered. That's going to come in, that's going to hit your eye, that's going to stimulate your optic nerve, and you're going to look at that and go, oh, great, there's a red dot there, okay? You don't see it in that transit, even if I completely turn out the lights, okay? So even if I turn out the lights, okay? If I do that, and turn this on, you still don't see that light. But if I do that same trick we did the other day, and I turn that on,
Wow.
and give that a spray,
You got water in there? Is that cool?
it's just cleaner. Okay?
Wait, so how come you can see it when you look into the light?
Because then that is hitting your optic nerve. So those photons are going directly to your optic nerve.
So everything we see right now is just photons?
So
Yes,
how
bouncing
Holy
off.
crap, that's kind of weird.
how does it reflect? Because I thought isn't matter mostly empty space?
It is. But it's interacting with the electrons.
Everything's not real.
So what happens with those photons when I do this, okay, Louis, for you to see it, okay? So, God, if anyone says air molecules, I will shoot.
My bad, bro.
Okay? Swear to God. Find air on the periodic table. Okay? So what's happening in that mechanism for you allowed to see that, what's happening is that those particles that make up that aerosol, those particles then have the capacity to take those photons that are being transmitted and going through them and bounce those photons off. The nitrogen and oxygen that make up air molecules, okay, don't, all right? And they just go straight through them. So if oxygen and nitrogen did have that capacity to do that with light, then when I did that, you would be able to see that beam. So nitrogen and oxygen, they allow that light to pass straight through it. The particles that make up that aerosol are big enough and they have a different chemical structure that those particles take those photons and make them scatter. That's how you can see that beam of light when I spray the aerosol, but you're not going to when I just shine it straight through.
So it's like magnetism almost?
Oh, no, nothing like
Or
that.
like charging what?
No. Okay?
How does everyone actually
Basically,
know what you're talking about?
in this situation, Louis, you can think of it, it's a visual. It's not this visual, but it's a visual. So imagine light being a stream of tiny little marbles.
Yeah.
Okay? So basically, if I do this, those marbles are going through the space between all the nitrogen and oxygen particles, and there's no interaction. Okay, so it would be like, let's say, that would be a deal like, you have a person who's just very, very reserved, okay? And they could walk through a party and not interact, okay? So it's like, hey, did that person go through? No, didn't see him, okay? Because he didn't interact with anybody. Now, Louis Evans shows up to a party, okay? Louis! What's up? Put your high five, right? Okay? Energy is being given off because you're interacting with that, okay? So that's kind of a similar type situation. So this is, hey, boring person walking through the party, not interacting with anybody. This, Louis, is in the party.
Louis!
See the difference?
Yeah, okay.
Okay, all right. Now, the actual mechanism has to do with how those photons get scattered off. So, let's say, for example, I have a mirror, right? See, I've looked at mirrors before, right? So, I'm going to take this light, and I'll shine it up there on the F equals MA, right? But, if I put this mirror in front of it, then that dot shows up over here. So, when I change that angle, okay, notice that I'm changing that location. So what's happening with any mirror, and I'll use the window over there in just a second. So here's a mirror. So when you talk about a mirror, as long as it's a flat mirror, and mirrors get weirder, I'll show you why in just a second. So when you talk about mirrors, as long as it's flat, we'll deal with curved surface mirrors later. When you talk about a mirror, you talk about what's called the angle of incidence and the angle of reflection. So if you go with the analogy of light being made of particles, so imagine that light comes in and it hits a wall. It's going to hit that wall, and then it's going to bounce off of it. So as long as it's a flat surface, okay, this is a huge if. As long as it's a flat surface, these two angles are equal. Your angle of incidence is going to equal your angle of reflection. So that I stands for angle of incidence. That's an E. Let me rewrite that. Angle of incidence, and then your angle of reflection, okay? So as long as it's a flat mirror, theta I is going to equal theta R, okay? Those two is pretty simple. So if you want to visualize this as you rolling a ball towards the wall, it's going to hit, and then it's going to bounce back. And these two angles are going to be identical, okay? As long as it's a flat surface. So let me turn the lights back on. Now, Roa, you're going to have to basically get behind me and kind of film behind me as I look into that mirror. Or
Okay.
That, okay? All right. Okay.
This mirror? Is this a mirror?
Right there. That glass right there.
Wait, what?
Okay.
Sit behind
So, Tracy, you're going to need your help.
Like over here?
No,
behind him.
Here.
My bad.
No.
Behind the mirror, is that what
That's what I was thinking. I was like,
Okay,
well, I
actually,
don't...
get back over there on the other side of.
What are mirrors made out of? You know what? I've always wondered that.
Yeah, it's glass. Okay.
It's glass with what?
Silver plating. Started. You ready?
Oh, yes, it's going.
Okay, all
I
right.
think, yeah.
So, this is where, and this is just a crude mirror, okay? But it's a glass. So what's happening here is what's allowing me to see my reflection is that here's your mechanism. Photons are being produced by the light, the excited states of electrons. Electrons go up, they don't like that energy level, they come back down, they kick off a photon. Photons come out, they bounce off me. They bounce off me, they hit that glass. Part of it goes through, and part of it is reflected back. So what I see are the path of these photons is actually like a double distance. So they're coming off me, they're hitting my shirt. They're bouncing off my shirt, they're going to that glass, they're hitting the glass, they're bouncing off that glass, and then they're coming back to me. Now, this is where this gets a little bit weird. So I'm going to raise my right hand, okay? So, now, whoa, that was weird. Or I put my hand down and then it does raise it up. Like, okay. But this is where it gets a little bit philosophical. So imagine that I raise my hand. Now imagine, this is the leap of faith that you have to have. Imagine there was an identical twin of me on the other side of that glass. Okay? That would be equal distance away. So if that was just a flat plane of glass, if I raised my right hand, okay, now visualize this. You're the twin on the other side of me. If I raise my right hand, if you're on the other side of me, to make this look the same, like I'm looking in a mirror, which arm would you raise?
Left.
You'd raise the left. Okay? So when I do this, if you're on the other side, you would be raising your left hand. Okay? So what happens is that when I raise this, if you're looking in that image, okay, and that's, let's say you can't see me, all you're doing is that you're looking at that. Which hand would you say the person was raising? Left. So here's the deal. So this gets flipped. If you imagine me on a vertical axis, okay? So if you imagine me on a vertical axis, when I look at that mirror, I'm being flipped on a vertical axis, okay? But what's weird is that, and thankfully, mirrors would get really weird, thankfully, I don't get flipped on a horizontal axis. Because if I got flipped on a horizontal axis, then I would look like I was upside down, okay? Which would get pretty tricky, right? It's like, oh, I'm trying to check my hair, or shave, worse yet, trying to shave. Imagine that you're upside down trying to look at your image, and that would just get really weird. Now, Gracie, can you see me? Mm-hmm. And I can see you. Okay? Now, I'm going to move. Okay? Now, can you still see me, Gracie? Okay? I can still see you, right? Now, I'm going to move over here. Can you still see me?
Yeah.
Huh? No.
I like the glass.
Okay. So if I'm here, can you see me?
Yeah.
You cannot.
I can see you. Yes,
I can see the fire alarm.
Put how many fingers you have up. Put some fingers
Well,
up.
no, put it by your head. I can see your head. Okay, now I can see you.
Okay.
Well, now I can.
Now you can't? Now you can't.
Okay.
Now, here's the story. When it comes to mirrors, you can see me? I can see you. So, when it comes to mirrors, imagine what's happening with this mechanism. So, that light is bouncing off me. So, imagine that we're going to draw a string from me to that glass. Then we're going to take that string and then we're going to pivot it over to Gracie's line of sight. Okay? So imagine we're here, we have a string, hits the glass, comes over here, right? Now, as long as Gracie is within that line of sight with that triangle, that string, she can see me. So I can obviously still see her because I'm pretty much right behind her. But here's my point. As I move further and further and further and further over, what happens, Gracie?
I can't see you.
Okay? But now, tell me when you can see me.
Oh, I've been able to see the whole time.
Oh,
Keep going.
The whole time.
keep going.
Keep going.
Keep going. Keep going.
Okay, yeah, you're good.
Okay? Can you see me now? Now, here's the thing. I can't see Gracie either. So, I know when Gracie's going to lose sight of me is when I can no longer see her. So, keep this in mind when you are passing a vehicle, especially like a large truck. If you look in the mirror, if you can't see the mirrors of that truck, they can't see you. Okay? That's the rule. So if you can't see something in a mirror, they can't see you either. So when I move over, then you can't. So what that means is that when you're looking at objects that you can view in a mirror. Now, Gracie, I'm going to move over here. You can still see me, right?
Mhm.
Can you see Vitor?
No. Person is the-
Might have to stand up. Vitor, stand up.
Yeah.
Okay? Vitor, you can still Vitor, right? Now, if I move over here, can you still see me?
No.
Okay? Now, I'm going to move in here. Can you see me?
Yes.
Can you still see Vitor?
Yes.
Okay? Still see Vitor?
Yes.
Okay? So, now, Vitor, I want you to do this. Come around the table. Okay? I want you to stand right there. Okay? Right? So, you can still see me, Gracie, right? Okay, I'm going to move over here. Can you still see Vitor?
Yes.
Can you still see me?
No.
No. But you can still see Vitor.
Yes.
So imagine this. So you draw a line from Gracie to that mirror, and Vitor is included within this triangle. Okay? So Gracie can see what's inside of there, right?
Uh-huh.
You can still see Asta behind you, right? Right?
Yeah.
But if I move over here, so just because you can't see me doesn't mean that you can't see what's inside of that triangle. Okay? Got that. All right. Well done. Thank you.
Oh, sorry.
You were so homecoming.
Oh, bro.
Mr.
Were you there?
Yeah.
So awkward at what?
Which one though?
Like
Both?
No.
Have to simply one.
Okay. Now. This one should.
Mr. Don't get nervous, like,
Hold on.
soccer, I get nervous, but that ball,
You got stage fright.
hey, that's weird, bro. They put the
Hey,
light
but
on
you
you,
know
bro,
when he
like,
goes to basketball
blind,
games.
bro.
Hopefully.
Well, that's better than being able to see everybody like that.
Okay. Now we'll shut the light out again.
Oh, man.
So many people.
I was there like, shit. That's why you shake. Let's get it.
Okay.
No, I don't think
So this is a thick piece of acrylic glass. Now, what I want you to do is, I'm going to shine the light over there on the wall, right? Okay? Kind of pick a spot right there. Now, if I put that acrylic where it's at a 90-degree angle to that, notice that that really doesn't move. Now, what I'm going to do though is I'm going to shine it up there, but then I'm going to twist that acrylic piece.
Oh, it's behind.
So when I do that,
There's like four.
what does it do?
There's like
Whoa.
four
It
of them.
reflects.
Yes.
Bro.
Okay. Now, but does the position of that light move when I twist the cube?
Yeah.
Oh.
Yeah. It's
Yeah,
right there on the
yeah.
board.
Yeah.
Okay. Quite a bit, right?
Yeah.
So what happens with light as it goes through an optically dense medium? So here's this piece of glass. So if I shine it straight on like this, okay, nothing happens. So in terms of the angle. So, but does the light slow down when it goes through that acrylic?
Yes.
Yes, because it's optically dense, right?
Yes.
The bigger the index of refraction, the more that it slows down. Now, here's the best analogy that I can give you. Is that, let's say that you're going to drive your car, right? And this is the top view, and here's your axle, okay? So you're driving along, and you are on dry pavement, okay?
Wait,
So-
so are we talking about something completely different right now?
Huh?
Are we like going away from the block?
No, we'll go back to the block,
Okay, so
okay?
should I draw this?
It's up to you. So imagine this is dry pavement. Now, this right here is deep snow. Okay? So you're here like this, dry pavement. As soon as you get into this region, you're in like a foot of snow. So, but now, you're coming in, this is going to be important. You're coming in at an angle, right? You're not at right angles to it. You're coming in at an angle. So as you come in at an angle, what's going to happen?
You're gonna straighten out.
Why?
Cause so when the right one hits first, it slows down first, and then it gives the left time to catch up.
Fantastic. So what's going to happen? Now, if you were going in at right angles, what would happen?
Nothing.
Nothing would happen because they would both slow down at the same time.
Yeah.
Right? But if you come in at an angle, this side's going to slow down first. So if you consider this a line, okay? What we call the line with the normal. So this is going to come in at a certain angle. Let's say that's 40 degrees. Pick a number. Now, when it hits, this side here is going to slow down. And then, when it slows down, it's going to get tilted this way. So what's going to happen is that that's going to get tilted more towards the normal. So if this is 40 degrees, that might be something like 30 degrees. Okay, so when it goes into something that's more optically dense, you can think of this as being like tires on a truck. It's going to hit, it's going to slow down. Now, you're in deep snow. And then over here, now you're back onto dry pavement. So you're here, right? You're in like this. This side slows down. You bend it like this. Now you're coming in here like this, right? Now when it hits dry pavement, now what's going to happen?
The opposite. Go back to
So this side is going to
free up.
and it's going to do what? And then it's going to go like that. So then, if that's the case, then that's going to speed back up. Okay, so light does the same thing. So light gets bent when it goes into more optically dense materials. So, we're going to go out to the fish tank, so bring the camera.
Wait, so this has nothing to do with mirrors, right? Only
No.
in things that are going through mediums?
Yes. So, Louis.
Aw, poor guy.
Go, Pop, go.
He asked for it. Okay.
Oh God.
Opinion.
I need the red.
Aw. That looks kind of ugly.
Okay. So,
Yeah, they're hard to see.
I need somebody to hold this just kind of like this. Okay? And then I'm going to take this. So, I need somebody to hold this right here.
It's all Jackson.
Not to invade your personal space.
Okay.
Sorry.
So what I'm going to do is I'm going to shine this light down parallel with the one that Aspen's holding. Okay? Now, so what I want you to see is that if that tank was just filled with air, when I would shine that light, what it would do is that I would follow that straight path and it would hit right here. So what's happening is that when I do that, you'll notice that that light actually hits right here. Okay? So what's happening is that light, instead of going straight through, it's that analogy with the tires. So imagine this light is coming in, and this is a set of tires. It's going to hit that water, that's going to slow it down, and it's going to bend it towards that normal. So then it's going to slow it down, and then it's going to hit here. Now, imagine that we had a glass bottom on that tank. So what would it do? Once it got out of the water, what would it do? It would speed back up, and then it would straighten back out, and then it would go like this. So if we had a glass bottom, what you would see is that you would see come in, boom, hit here. Then when it came out of that, then it would speed back up, and then you would have a parallel line with this line here, parallel with that one. So what you'll see is like, it's just like water versus thick mud. The more optically dense this is, the more it's going to bend that light, because that's going to be more of a difference on that speed. Got it? Good? Okay, back we go.
I know.
So what this is kind of cool, and I'm going to tell you right now, it's a little optically weird. So what I'm going to do is I'm going to pass this around. So this is just a cube, but it's coated as well. So when you look at it, if you just hold it like up to your finger, and then twist it without moving your finger, what you'll see is that your finger can almost like disappear and certainly shift how you view it. And depending upon how you set this up, it's going to look different. So if you look at it just square on, okay, if you just look at it square on, it just looks blue. But if you begin to tilt it, you can change, it almost looks like your finger gets cut off and it begins to move. So you can look at it through different colors, and even if you look at like the lights, and if you do anything with that, then it gets a little bit trippy because of the fact of the way that those lights are interacting as it comes through these surfaces. So,
It still hurts your eyes if you can't see it, but with that.
huh?
Does the light still hurt your eyes if you like can't see it anymore with that thing?
It's
Oh.
like saying you're shining a light through that and it.
Does that hurt your eyes still?
Well, if you can't see the light, then no.
What?
Like if you said that you can look at the light and it'll like disappear.
Wait, that's
The lights
weird.
Yeah, so if you had a laser that could do that, yes. But you
Does it
just,
have to do with the color?
huh?
Does it have to do with the color? Or
What do
is
you mean,
it?
like how it changes? No, the color just gives it like a different pigmentation.
So then what's doing it?
What you're doing is that as you're changing
Yes.
that angle, okay, you're changing how that light is getting reflected off of that. So, that got a little bit weird. Okay, so here's the math so far.
There's math.
Math, just a little bit.
Math. Math and physics does not equal. And one sine theta one.
And
Why
one.
do they want me?
You sign up for college credit. It's probably to get your stupid Newman. If you send it.
Oh my god, I need to sign up for college credit for English.
That's stupid.
That's due tomorrow.
Yeah, yeah. Let me set myself a reminder. Hey, set a reminder for 10 p.m.
Is that like, is that N? Is that
N1 sine theta 1 equals N2 sine
Sign
theta
up
2.
for Newman credit for English.
Angular momentum.
Close to that.
Okay. Sorry, what?
You really
What
want
did they say? What?
You were saying about how you were complaining about your 86 and Connor sitting back here listening.
what Connor get?
Connor passed.
I don't know if I did.
Did you not calculate the percentage?
No, I don't want to.
Just tell us the number 1 to 80 what you get.
Okay, so what you have here, imagine that you have a light that's coming in here and it's going to hit this.
Is that in or
Yes.
wavelength?
So this would be like air, all right?
Oh, like the, what's it called thingy that we
Index
just did?
of refraction.
Yeah.
Okay, so this is air, it has an index of refraction of 1, okay? Cool with that? Now, what's gonna happen is that this is gonna be glass. So let's say that that glass here, this pane of glass, has an index of refraction of 1.50. So what we wanna figure out is what's gonna be that new angle. Yes?
What do you mean by always from the normal?
The normal is the line that's like at 90 degrees to the surface. So this is your line that's normal.
To the surface of
Yes.
what? Like the
To the
ground?
surface of the glass or whatever the light's going into.
If it's called normal.
Oh,
it's
so
probably
like if
different.
it was going through like a window, it would be this would be the normal?
Yes,
Okay, that makes sense.
yes. It's just like if you imagine like, remember when we studied like weight and gravity was acting straight down and the normal force would act straight up
Yeah.
at right angles to the surface. If you were on an inclined plane, the normal was like this. The force normal was
Oh,
always
yeah.
at a right angle to it.
Yeah.
That's what that's referring to.
Okay.
Okay? So, light's going to come in at an angle of 30 degrees. So if you go with the wheel analogy, so this ray of light is coming in here like this, right? It's going to hit here. So which direction is it going to be bent? Is it going to be bent towards the normal, or is it going to be bent away from the normal? Towards or away?
Away.
So as this comes in, it's coming in like this.
Or no, towards.
Okay, you go towards the normal.
Wait, the N is getting
So
bigger.
imagine this is the wheel on
So
your car.
Sandina has to
So you
get.
go towards.
You're gonna come in here.
Towards.
Is this end gonna slow down first?
Slow down.
It's gonna slow down, right? So then what's it gonna do?
Small.
Gonna go
Small
towards
angle.
the normal. So what I'm gonna try and find
Yes.
is what's gonna be that angle. So if it comes in at 30 degrees, what do you know about that angle? What does it have to be less than? 30 degrees. So this is what's known as the law of index of refraction. So in this situation, typically how these problems start, you typically start with them starting off in air. Okay? Just like what I did with the fish tank. Okay? I'm going to start off in air. So my N1 is going to be 1. I'm going to know that. So I'm going to have 1. Then I'm going to know the sine of 30 degrees. I know N2 is going to be 1.50. And then I'm going to have sine theta 2. So how am I going to get that angle by itself?
Inverse sign.
Well, I got to do what first?
Divide
I got to divide by that second index of refraction, and then take the inverse of that, right?
Wait, so what is N?
N is the index of refraction, just what we talked about on the last test.
Oh, okay, I gotcha. Sorry, I thought it was like a distance of something.
No. Just the index of refraction.
Gotcha.
Just like what you did on the test before.
What do you mean by always from normal then?
We just asked them.
The line.
So
No,
this
I
angle
understand that.
is always going to be measured from 90 degrees, not from the, it won't be the angle from the glass.
No, I get that, but you pointed to the N when you said always from normal. Can the equation scroll up?
No, the normal is just referring to like an imaginary line that's at right angles to the surface.
Okay, I get that. It has nothing to do with N though, right?
No. That normal and N1 has nothing to do with each other.
Okay, cool. That's
Okay? These ends are just indexes of refractions, Louis. That's all they are. That has nothing to do with that. Okay? All right. So what'd you get? I just made this up. So what'd you get for that angle? What'd you get?
19.47.
So 19.5 degrees.
That was a green.
Okay? Now, hopefully that makes sense that that angle was less than 30 because it came in, slowed down. Now, so what we had, so here's this plane of glass, right? So it's going to come in here. Here's this normal. So it came in at 30 degrees, and then it got bent, and then it's going to come out at a different angle of 19.5 degrees. Okay? Thank you. Actually, let me redraw that. I'm going to draw it a little bit
Oh yeah,
bigger.
that was like sitting. Remember, that's the shirt I found in this spot.
Have you seen it when he like runs over all of some of the Xbox games with the track?
Who likes the shirt here?
That's disgusting.
It's got
Okay, so this came in at 30. Once it hit, and this represents that big gap there, that's the glass. Okay? So it came in, hit the glass, got reflected this way. Now, it's going to travel through the glass. Okay? Now, what I want to try and figure out is what's going to happen when it leaves the glass and goes back out into the air. So, if this is 19.5 degrees, what's this angle going to be?
30. Oh,
Wow. 19.5.
my bad. I was talking about.
Wait, so that's just the angle that's in the glass, so it hasn't left
Oh,
yet?
it's
No,
like,
no.
isn't this like?
So, this whole thing is representing this big chunk of glass.
So that's, oh.
So it came in at 30 degrees, right? It got slowed down and it got bent to 19.5 degrees. So this point is going slower because it's more optically dense, okay? Now, then it's going to hit the glass. So when it hits the glass, what's going to happen?
Straight back out.
Wait, so if that's traveling?
Now, well, let's see if it does. So now, when it hits the glass,
That might not.
if you're going from N1 sine theta 1 equals N2 sine theta 2. So this N1 we said was what, 1.5?
Yeah.
So 1.5 times the sine of 19.5 is going to equal N2, which is air, which is 1.00, times sine of theta 2. So I'm going to divide by 1 and then take the inverse of all of that.
30.
And oddly enough, you'll get back to 30 degrees.
Dang.
Okay?
So, is that just law of science?
Kinda.
Kind of.
Yeah. So then that's going to speed back up, and then that's going to end up at
Yeah.
30 degrees. Got that? Okay. Now, and one of the problems you're going to have on your homework, you're going to do like a trick shot.
Yeah.
We're gonna do a trick shot.
Kind of.
Perfect.
There's this guy on Instagram Reels that does
Dude,
trick
you should
shots.
start, like,
and he's
all-
like, do you know who it is?
Yeah.
He's like a little kid.
The little kid? Nah.
What you do with all the towels and
I
with
thought you were talking about the one that got all the balls in the
Espudo?
bag and throws like when you said it
Right.
I don't know. No, there's a kid and his mom that always do like trick shot competitions, and every single time whenever he ends his video, he's like, "Oh my god, I just hit that trick shot. That was so hard. Like and comment for the next one." he's a funny guy. And he gets like 1 million views. Other guy, it's not even hard trick shots. It's
the
just
delay
like,
Okay.
switches are terrible.
So, I've got a plain glass mirror right here. So I've got my laser. So if I shine this, okay? Now, notice that that's hitting a point over there on the cabinet.
So,
Okay? Now, so notice that as I change this angle,
Where?
now I'm back to mirrors. So as I decrease that angle, what happens to that red dot?
It gets closer to 9.
Closer to 90, right? So if I'm over here, so here would be the problem. Imagine that I'm over here, right? And I'm going to shine this light on that mirror, and I'm trying to hit like that blue shirt. So imagine I'm like this, okay? So oh, that's in the way. Oh,
oh my god.
okay.
Watch your language.
where's it going, man?
So
You've
where did it
missed.
go?
It's hitting the
Some
chair.
Practice going on.
It's on the chair.
Oh,
Oh, that was close. Up.
the paper's gonna block it.
Okay. So,
It's very shaky.
and it's tough to do.
Yeah, you do it, Sam.
Okay, now, so now, here's what you want to look at.
Try this I can.
So this would be like the trick shot. So like, here's gonna be the basic idea, is that imagine like this is this room, okay? And, let me go over here.
I know it's fine too.
No, it's not.
So that mirror is here, and I'm like this, and then it's going to bounce off, and it's going to go something like this. Now, what do you know about these two angles? That angle of incidence has to equal the
Angle of refraction.
angle of refraction. Now,
Yes.
so this is kind of a geometric application. There's a couple of ways you can do this.
Geometry.
So if you look at this in terms of a triangle, right? So this is going to be a right angle, that's going to be a right angle. So if those two angles are the same, so if you look at this in terms of tangent, so that tangent of that angle is going to equal, if you would call this y1 and call this x1, it doesn't make it, I'm just going to call it y1, x1. So that tangent of that angle of incidence is going to equal y1 over x1, right? Now, this angle in here, that angle of refraction, has to equal x2 over y2. But if these two angles are the same,
Oh.
oh,
Y1 over x2 equals x2 over y2.
yes, because the ratio has to stay the same.
Oh, so that means you can like do the cross multiplication.
Oh, maybe something like that. It's a possibility.
What a math nerd.
Now, you just keep that in mind when you get to one of the problems on your assignment. You keep this concept in mind. Okay.
Wait, come back.
What?
Can I write that down?
Write that down, write that down. Write that down, make a noise. Write that down, write that down.
Wait, y1 over x1, x2 over y2?
You were Patrick impression. That was pretty good.
Because, bro, look, it's tangent, so it's like.
What is happening?
Just hold on.
We got you in person.
Is it a candle?
Yeah, it's a candle.
Why am I light? Oh, okay, I forgot.
What do you forget, Louis?
To get to believe. That sucks. Happens to the best of us.
Happens to you.
Now we're talking about reading, and it's gotta go manual now.
Switch to manual mode.
Yeah, stop.
Wait, so
Turn
aren't their
on
x's the
automatic
same?
reading. Start talking about it and then you stop.
The ratios are the same.
Oh yeah.
No, think about it.
I guess my triangles are the same size.
Yeah,
Yeah,
I'm
read it
reading
normal.
automatically. Yeah.
Now I'm thinking about it.
Yeah, and then you have to.
Okay, now, we'll get more into this tomorrow and the difference between what we call a real image and a virtual image. So a large part of optics is the understanding of the terminology. So when you look at a mirror, okay, what you're looking at is, if you think about it, if it's a candle or whatever it is, that candle basically appears like it's on the other side. A lot of times when you do optics, and this goes back to the old schools, because when they were studying optics in the 1800s, they didn't have lights. The only thing they used was candles. So when you look at a lot of diagrams in optics, they still use candles. As a matter of fact, when you look at, you measure the output of light, it's measured in candles, which was basically a measure of, hey, how many candles would it take to get a certain amount of light? Okay?
Like horsepower?
Kind of like same idea. Same idea. So when I was looking at that mirror, basically what it looked like that there was a symmetry. So it looked like if I was, say, 2 meters in front of that mirror, it looked like there was another one of me that was 2 meters on the other side of that mirror. Okay? But if you've ever looked in a mirror, you can look down and you can see like your feet, you can see your belt buckle, you can see your hands. It isn't like you can just see your eyes. So if you look at what has to happen for you to see, this is going to play out in one of the problems. So what's got to happen is that it's going to look like, it's almost like the hypotenuse of a triangle. So if you're going to, let's say you have a full-length mirror and you're looking at your shoes in the mirror. So that light is going to look like it emanates from your feet, but it's really happening is that it's bouncing off your feet, it's hitting that mirror, and it's bouncing up. But it's going to look like it's on the other side. So if you're standing in front of a mirror, full-length mirror, okay, so here's Louis, he's getting ready in the morning, okay? So here's his shoes, okay?
The mirror's a little tall.
That's okay, go.
It's like a 7-foot mirror.
Back on. Okay, so Louis looks down,
It's just a normal size.
and Louis sees his shoes in the mirror, right? But if you look at the path of what's going to happen, that light was bounced off of his shoes, goes up, hits the mirror, goes to his eyes, but now Louis' eyes are going to translate that back, and Louis' eyes are going to think it looks like it's on the other side of that mirror. When you look at a mirror, and this gets a little, I'm going to tell you right now, it gets a little bit tricky because you never look at mirrors the same way. Because when you're going to look at them, you're going to think, oh man, it looks like I'm on the other side of that wall. And so what's going to happen is that Louis' perception is actually going to look like, wow, those shoes are on the other side. So the distance of that appears is the hypotenuse of that triangle.
So it's double?
Well, yeah, basically. As long as it's a flat mirror.
Wait, I'm confused on why when you said that your eyes translate it.
So here,
So
so
after it hits your eyes, what happens?
hold on. Let me back this up. So here's what I want you to, no pun intended, see. Okay? So imagine that there was a Louis standing on this side, and this was just glass. Okay? It wasn't a mirror. Right? Just wasn't glass. So if a photon comes in here, it's a huge photon, and bounces off Louis' shoes, it would go straight up to his eyes, and that would be that path. If there's a mirror, that photon comes up, hits the mirror, bounces off, goes like this. Louis' eyes can't tell the difference. He can't tell the difference if that photon comes in here, hits that mirror, and bounces off, or if there's another Louis on the other side emitting that light. Because what his eye is going to do, his eye is going to trace it back to the origin. So that Louis' eye is not going to be able to tell the difference between whether that photon hit that mirror and bounced this way, or if there was just another Louis on the other side and it was bouncing off that and going straight through the glass. Okay? Just wanted to point that out. Okay, I'm done. It's a relatively short assignment.
When you
Just
say
telling you.
relatively,
Relative.
We
He
get
said the last
15.
one was super short.
means it doesn't exist if we look at it, right? It's kinda-
It could be a virtual or a real assignment, whatever you want to play it.
Virtual. It's only the
Do
third
this
week of the
anymore,
semester.
Said we have to. What? I'm still
Like the
stuck on
third
fact
full
that
week,
you
yeah.
said you have to
Bruh.
read manually, and you-
We had 2 tests.
everybody talks about it.
When's our next test?
Oh, it's going to be a while.
Okay, good.
Well,
We have
that's not good.
literally 3 labs back to back to back.
Okay,
It's true, bro.
I mean, it's gonna be a bad test.
I don't know. I feel like labs are good.
It works like
Maybe?
if you picture like your toes touching in your stomach.
What?
For me, it's so disgusting.
Yo, what the?
Talking about?
Like if I just,
Keep that to yourself.
Talking
You're
about.
like, got a right
I
to
can
it.
just like,
Chill,
if I
chill
like
out.
think about it, it just like
If you
annoys
touch
me.
your toes and your
Like
socks.
you can feel your toes rubbing against each other.
Yes.
I hate that.
I feel like
I hate
And it
it.
makes
So
you
you're telling me
manually
if I start
No,
talking
it
about
makes me
breathing,
think about it.
Whoa.
you don't start manually breathing, bro?
Never forget.
You don't start manually breathing? Like you still
No,
just breathe
bro.
slowly.
If I hear somebody say breathe, I'm just breathing automatically. I'm not breathing manually.
No, Vitor's
You
right.
start breathing manual.
Manual
We know what you mean. Sam's just being a
This
conservative.
guy's kryptonite is gonna be in soccer. Breathing manually. People tell me to breathe.
People are just gonna run to you.
Tell me to
breathe.
breathe.
He's like having a panic. I wasn't breathing the whole time. He's like purple.
Uh,
What is number
Oh my
9?
god, that's so big.
Oh dear God.
Is that A or 9?
A. Mr.
Someone said A.
I say you really have the gift of artistry.
it's 8A.
Yeah.
No,
Oh,
like
that
the,
says
the
9.
bottom left.
Number 9.
No, this is referring to number 9.
Okay.
Oh.
Are you gonna do it with us?
No, but I'm gonna get you a really solid start on it.
Okay. Johnny boy.
Should I just do it first then?
As long as you put it in the right sequence.
Oh, I don't. Never mind.
What if I just did all the problems, but they were just in a random order?
Oh,
I do that in calc.
Is 8B
Well,
bad?
yeah.
You do what kind of portal?
Well, I just do the easiest ones first.
Oh yeah, 100%.
okay.
But I can't
So-
do that in here.
And this is starting on page 595, Lou,
Thank you
just
for
for
that.
you.
Thank you for that.
Page 595. Okay? So let me explain what's happening on number 9. Okay? So number 9, you have a diver that's underneath the water. Okay? And he's going to see the sun 50 degrees above the horizontal. So you have to, on these, it's handy if you can visualize what's the path of the light. So here's this diver down below. Here's the sun. So what you're told is that the diver sees the sun 50 degrees above the horizontal. So according to him, when he sees this light, this is 50 degrees above the horizontal. So imagine he's down here, you're below the water level, okay? You're going from water, and you're going to have to go back and reference those indexes of refractions, okay? So if you're here, he looks, to him, it looks like the sun is 50 degrees above the horizon. So what you're asked to find is how high is the sun above the horizon to a fisherman in a boat above the diver? So imagine that you're up here, okay, and here is a fisherman. Imagine that he's basically right at that same level. So what you want to know is if you're the fisherman above the water, what angle are you going to have? Okay, so in other words, the diver sees it at 50 degrees. If you're on the boat looking at it, are you going to see it at 50 degrees? Is going to see it above 50 degrees? Or are you going to see it below 50 degrees?
What's the normal? Does he have a different normal?
Now, no. So remember, that 50 degrees, right? Anything with those trig identities has to be with the normal, which is going to be like this.
Wait, so what about the other dude?
Well,
His normal is flat, 180?
What? Their normals are the same.
the
Why?
normals are the same.
Because they're both, it's,
They're not looking through glass though, they're looking up.
One's underwater. Maybe.
So here's the
Yeah.
point.
It's the same thing. It's like he's in the glass.
Wow.
So the fisherman, the fisherman, right? There is no glass involved, because for the fisherman, that light is only traveling through air.
But how are you supposed to know the
for
angle?
the diver,
Oh, I guess they tell you probably.
for the diver, it's going. That light has to go through the air, hit the water, and then get bent. There is no bending for the fisherman, because the light is only traveling through air.
what angle? Okay.
But how are you supposed to find the angle from that?
That's
The equation we just had got.
I know, but if there's nothing for it to bounce off of.
It's not bouncing. It's like
It's
the
not
fish tank.
bouncing.
I know, that's what I'm saying. If you're like looking, like it kind of just
It's
depends
like the
on
wheels
what.
in the snow.
It's
wheels
the
on-
water.
wheels
It's
on the
just
bus
gonna
go-
change when it hits the
Go
water.
round and round.
Yeah, the wheels on the bus go into the tree. One of the two. The wheels on the
Just,
bus go-
no, just,
Okay, I'll be in here.